Hi everyone, I'm Evan and welcome to Lesson 3 of National AI Youth Council's AI Education Curriculum, Deep Learning and Neural Networks. So far, we have covered Introduction to AI and Machine Learning. The goal of today's lesson is to talk about deep learning and neural networks. We'll break this down into four key sections: artificial neurons and layers, backpropagation and gradient descent, loss functions, and finally, convolutional and recurrent architectures. By the end of this lesson, you'll have an understanding of deep learning and neural networks and how it works. So let's dive right in. So before we start, we have a activity, a warm-up question, as you can see on the slide. So some real-life scenarios where computers or apps can make predictions based on patterns. Let's take a moment to think about this. Imagine you're using your favorite app, whether it's for music, videos, shopping, or even studying. Have you noticed how it sometimes seems to know exactly what you want? What do you think might be happening behind the scenes to make that possible? As we discuss today's topic, think about how these ideas might connect to the way technology learns from data around us. Take a moment to pause and reflect. What are some real life scenarios where computers or apps can make predictions based on patterns? Go ahead and pause the video now to write down some of your own ideas. We'll talk about them in a minute. Okay, now that you got some time to think about it, let's discuss some possible answers. So these are the possible answers. Uh, Online shopping recommendations. So when you browse products on an online store, the system analyzes your clicks and searches to recommend items you might be interested in. This happens because the app or website looks for patterns in your behavior and matches them with other users who had similar preferences. Another possible answer is navigation and traffic apps. Navigation apps like Google Maps predict traffic conditions and suggest faster routes. They analyze data from other drivers and historical patterns to make accurate predictions about travel time and congestion. Lastly, another possible answer is healthcare predictions. In some hospitals, systems can predict potential health risks or complications based on patterns in patient data, like heart rate or medical history. This helps doctors intervene earlier or provide personalized treatments. All right, now that we've answered the question, let's get into our lesson for today. So first, we'll be talking about artificial neurons and layers. So imagine a neuron as a tiny, intelligent decision maker. Like a diligent worker, it receives signals or inputs from various sources, each signal carrying a certain importance or weight. The neuron meticulously adds these weighted signals, and if the sum reaches a certain threshold, it fires or activates, sending a signal output to other neurons. This process is mathematically represented by an activation function, which adds nonlinearity, enabling the network to learn complex patterns. Think of it like baking a cake. Each ingredient or input has a specific quantity, weight, and the oven activation function transforms the mixture into a delicious treat output. Just as your brain uses a network of interconnected neurons to think and learn, artificial neural networks connect these artificial neurons in layers to perform complex tasks like recognizing images, understanding speech, or even translating languages. So, now that we're acquainted with artificial neurons, let's explore how they collaborate. Next up, we'll be talking about how to structure artificial neurons. Here, we'll unravel the different types of layers in a neural network and how they work together to process complex information. Think of neural networks as an assembly line in a factory. Raw materials enter the input layer, just like ingredients for a delicious dish. Then, they move through a series of processing stations called hidden layers, where each station or neuron performs a specific operation, refining and transforming the data. Finally, the finished product emerges from the output layer, ready to be used. For instance, in a network designed to recognize cats in pictures, the input layer receives the image pixels as raw data. Hidden layers then act like detectives, with the first layer detecting simple patterns like edges and lines. Subsequent layers combine these findings to identify more complex features like eyes, ears, and fur. The output layer then makes the final decision: is this a cat or not? The more layers we have, the more intricate the features the network can learn, allowing it to tackle complex tasks like image recognition, natural language processing, and even medical diagnosis. So you might be wondering why layered structure is so important. Take a moment to think about it. In this section, Advantages of Layered Architecture, we'll discuss the benefits of organizing neural networks in this way. Any ideas? Think about it. Okay, let's move on. Imagine trying to build a house by throwing all the bricks, wood, and wires in a pile. It wouldn't work, right? Layered architecture brings order and efficiency to neural networks. Firstly, they allow these networks to scale, handling massive datasets like the internet or large image repositories. This scalability is crucial for training powerful models that can learn from vast amounts of data. Secondly, they enable hierarchical feature extraction. Early layers act as the foundation, finding simple patterns like edges in an image or basic sounds in speech. Deeper layers then build upon this function, combining the simple features to recognize complex objects, like faces in images or words in speech. It's like building with Legos, starting with simple blocks to create complex structures. Finally, this layered structure is incredibly flexible and adaptable for various data types, from images and text to audio and time series data. This flexibility makes neural networks a versatile tool for diverse applications, from self-driving cars and medical diagnosis to financial forecasting and personalized recommendations. The next part of this lecture will be about backpropagation and gradient descent. Okay, now let's dive into gradient descent, a crucial algorithm in training neural networks. Imagine you're standing on a hillside and want to reach the bottom of a valley. You don't have a map, but you can feel the slope of the ground beneath your feet. Gradient descent is like taking small steps downhill, always moving in the direction of the steepest descent. In context of neural networks, the hillside represents the loss function, which measures the error of the network's predictions. Our goal is to find the lowest point of this function, where the error is minimized. The steps we take are adjustments to the weights of the networks. There are different types of gradient descent. Batch gradient descent uses entire datasets to calculate the direction of the step. Our goal is to find the lowest point of this function where the error is minimized. The steps we take are adjustments to the weights of the network. There are different types of gradient descent. Batch gradient descent uses entire dataset to calculate the direction of the step. Stochastic gradient descent, or SGD for short, uses only one data point at a time, making it faster but less accurate. Mini-batch gradient descent strikes a balance by using small batches of data. The key equation for gradient descent involves the current weight, the learning rate, which determines the size of the step, and the gradient of the loss function, which indicates the direction of the steepest descent. By repeatedly applying this equation, we gradually guide the network towards the optimal weights. Think of it like finding the perfect setting on a complex machine. You start with initial settings and make small adjustments based on the output. Gradient descent provides a systematic way to fine-tune the network's parameters, leading to improved performance. Underst- Understanding gradient descent is essential because it's the engine that drives the learning process and many neural networks. By mastering this algorithm, you gain valuable insights into how machines learn from data. Sorry. Okay, so next we will have an activity. So for this activity, you will need to analyze three AI-generated images. Your task is to think about what kind of data the neural network was trained on and how it might have generated these results. Go ahead and pause the video in 1 second and write down your ideas. Take your time to carefully analyze each image and write down your thoughts. We'll go through the answers once you're done. All right, now that you have a chance to think about it, let's go through the possible answers and the explanations behind them to ensure a solid understanding. So, for the first one, a futuristic cityscape was likely generated using a dataset of like cyberpunk art, sci fi illustrations, and architectural renderings. The AI recognized common themes such as neon lighting, floating structures, and digital constellations, combining them to create a visually stunning and technologically advanced environment. The patterns in this image, including the glowing streets and intricate skyline, suggest that the AI drew inspiration from cyberpunk and utopian/dystopian aesthetics, producing a blend of realism and fantasy that aligns with futuristic world building. The second one is an enchanted forest that appears to be influenced by fantasy landscapes, nature photography, and mystical themed digital painting. The AI incorporated common elements of fantasy art, such as glowing trees, floating orbs, and a mysterious mist, to evoke a magical and ethereal atmosphere. The patterns observed in this piece include luminous flora and surreal ambience, demonstrate how AI associates fantasy settings with soft lighting, otherworldly hues, and an overall dreamlike effect. This showcases its ability to emulate artistic styles that emphasize wonder and enchantment. The abstract geometric artwork is a fusion of the the next one is an abstract geometric artwork and is a fusion of modern digital art, geometric designs, and the principles of color theory. The AI constructed a intricate mosaic of shapes, vibrant colors, and layered composition that reflects human-created abstract art. The patterns in this image, such as the symmetry, color contrast, and structured yet fluid design, indicate that the AI understands and mimics artistic composition techniques. This piece highlights how AI can interpret and generate abstract visuals from that balance randomness with calculated design, reinforcing its potential in creative applications. Next up, we have loss functions. So, moving on. So, what are loss functions? Why don't you take a go at this? Pause for a moment and jot down your own definition of what a loss function is and what you think its purpose in machine learning. Don't worry about getting it perfectly right. Just try to articulate your current understanding. Once you've written your definition, compare it to the one below. Oh, sorry, I don't have it. Okay. Are you guys done? Okay, if you're done, the definition is a loss function quantifies the error between the predicted output and the actual target. The purpose of it is to minimize error and improve the model's performance. So the key equation is listed below. So now that we have covered the basics of neural networks, we can talk about loss functions. So imagine you're learning to throw darts. Your goal is to hit the bullseye every time, but initially, your throws might be off. To improve, you need a way to measure how far your darts land from the bullseye. That's what a loss function does for your neural networks. It measures the error between the predicted output and the actual target. The lower the loss, the better the model's performance. There are different types of loss functions, each suitable for different tasks. For example, in a classification problem, we might use cross-entropy loss, while in a regression problem, we might use mean squared error. The choice of loss functions depends on the specific problem and the desired outcome. By minimizing the loss function, we guide the training process and help the model learn the correct patterns from the data. This is crucial for achieving high accuracy and building effective machine learning models. Okay, now let's dive deeper into the different types of loss functions. Remember, a loss function is all about measuring the error between predictions and actual values. but how we measure that error can differ depending on the type of problem we're tackling. Think of it like this. If you're trying to predict a continuous value, like the price of a house, you'd use a different ruler than if you're trying to categorize something, like whether an email is spam or not. For predicting continuous values, we have loss functions like mean squared error and mean absolute error. These focus on the difference between the predicted and actual numbers. On the other hand, for classification tasks, where we're sorting things into categories, we use cross entropy loss and binary cross entropy. These focus on how well the model is assigning probabilities to the different categories. The key takeaway here is that the choice of loss function depends on the nature of the problem. We'll explore these different types in more detail later, but for now, just remember that they all serve the same purpose, guiding the model towards making better predictions by measuring the error in different ways. Now that you have a good understanding of the different types of loss functions, the next question is, how do you choose the right one for your specific problem? Well, it's like picking the right tool for a job. You wouldn't use a hammer to screw in a light bulb, would you? Similarly, different tasks require different loss functions. First, consider the type of task. Are you dealing with a regression problem, predicting a continuous value, or a classification problem, categorizing data? This will narrow down your options significantly. Next, think about potential impact of outliers in your data. If you have outliers that could skew your results, you might want to consider a loss function that is more robust to them, like mean absolute error. If your model is designed to output probabilities like image classification, then cross entropy loss is often a good choice. Finally, for more advanced tasks, you might need to explore specialized loss functions like hinge loss for support vector machines, or even design your own custom loss functions tailored to your specific objectives. The key takeaway here is selecting the right loss function is crucial for building effective machine learning models. By carefully considering the factors we have discussed, you can make informed decisions and guide your model towards optimal performance. Lastly, we'll be talking about convolutional and recurrent neural networks. Standard In this part of the lecture, we'll cover convolutional neural networks, or CNNs, and recurrent neural networks, or RNNs. Standard feed-forward networks, while versatile, can struggle with data that has a specific structure. Imagine you're trying to understand a photograph by only looking at the pixels in a random order. You'd miss the crucial spatial relationships that make up the image. That's where CNNs come in. They're designed to understand spatial hierarchies like those found in images. They use convolutional layers, which are like tiny features, detectors that slide across image, learning to recognize patterns at different scales. This allows them to build up a hierarchical understanding from simple edges to complex objects. Think of it like how our brains process visual information, starting with basic shapes and gradually recognizing more complex forms. Now, what about data that unfolds over time, like a sentence or a musical piece? Here, the order of elements is paramount. For this kind of sequential data, we turn to recurrent neural networks, or RNNs. They have a memory of previous inputs, allowing them to understand the context and dependencies between elements in a sequence. It's like how we understand a sentence, not just by the individual words, but also by their order and relationship to each other. RNNs excel at tasks like natural language processing, speech recognition, and even predicting stock prices. In essence, CNNs and RNNs are specialized tools, each designed to tackle a specific type of data. CNNs are the masters of spatial data, while RNNs are the experts in sequential data. Understanding their strengths and weaknesses is crucial for choosing the right architecture for your machine learning task. We talked about the power of CNNs, but like any powerful tool, they can be misused. One common pitfall is overfitting. So, what exactly is overfitting? Imagine you're studying for a test by memorizing all the answers to the practice questions. You might do great but on the practice test, but then bomb the real thing because you haven't actually learned the underlying concepts. That's essentially what overfitting is. In the context of CNNs, overfitting happens when the model learns the training data too well, including all the noise and irrelevant details. It becomes so specialized to the training set that it fails to generalize to new, unseen data. Think of it as model memorizing the training examples instead of learning the general patterns. How can you spot overfitting? Pause and take a moment to think about it. The key to spotting it is to keep your eye on training and validation performance. If you see a large gap, like the one seen in the picture below, or if the training loss continues to decrease while validation loss starts to increase, you're likely overfitting. It's a sign that your model is becoming too complex and is starting to memorize the training data rather than learning to generalize. Overfitting is a serious problem because it prevents your model from being useful in the real world. We'll discuss the technique to combat overfitting later, but recognizing the signs is the first crucial step. Now let's explore some techniques to combat overfitting, collectively known as regularization. Regularization methods are like guardrails that prevent our models from being too complex. They help us find a sweet spot where the model is complex enough to learn the underlying patterns, but not so complex that it memorizes the noise. One popular technique is dropout. Imagine you have a team of experts working on a problem. Dropout is randomly taking some of those experts offline during training. This forces the remaining experts to pick up the slack and become more versatile. In neural networks, dropout randomly deactivates neurons during training, preventing the neuron from relying too heavily on any single neuron and encouraging to learn more robust features. Another set of regularization techniques involves adding penalties to the loss functions. L1 and L2 regularization are like adding constraints to the sculpture. L1 encourages sparsity, meaning it pushes some weights in the network towards zero. This effectively performs fe- this effectively performs feature selection, simplifying the model. L2, on the other hand, penalizes large weights, preventing the model from becoming too sensitive to small variations in the training data. Finally, we have early stopping. Imagine you're training a marathon runner. You wouldn't want to keep you wouldn't want them to keep running even after they're exhausted, right? Similarly, with early stopping, we monitor the model's performance on a validation set and stop training when the validation performance starts to decline. This prevents the model from continuing to learn noise and overfit to the training data. Regularization techniques are essential tools in machine learning toolbox, but understanding and applying these methods, we can train more robust models that perform well in real world. Conclusion. So we've covered a lot of new information today. Think about the core concepts of deep learning from the fundamental building blocks of artificial neurons and layers of to the complexities of back propagation, and gradient descent. We've explored the crucial role of activation functions in introducing nonlinearity and enabling our models to learn complex patterns. We delved into the world of loss functions, understanding how they quantify the error between predictions and actual values, guiding the learning process. We examined different types of loss functions, each tailored to specific tasks, and discussed how to choose the right one for your problem. We also tackled the critical issue of overfitting and learning about powerful regularization techniques like dropout, L1, and L2, and early stopping to combat it. Finally, we ventured into the realm of specialized architectures, convolutional neural networks, CNNs for image data, and recurrent neural networks for sequential data, recognizing their unique strengths in handling structured information. Understanding these components and their interplay is key to harnessing the power of deep learning. Let's take a moment to reflect on what you learned today. Write down your answers or just think about these reflection questions. How do concepts of backpropagation and gradient descent work together to enable a neural network to learn? Can you explain the process in simple terms, perhaps using analogy? Imagine you're building a model to classify images of handwritten digits. Which type of neural network architecture would you choose, CNN or RNN, and why? What are some key considerations when selecting a loss function and applying regularization techniques in this scenario? Next time, we'll think about these questions in more depth and dive deeper into our next topic. I hope you enjoyed this lesson and make sure to check out the next one. See you next time, and thank you for listening.